Hi everybody, it's Professor Mitchell, and today we're talking about section 1.2, which is types of data. Another vocabulary section, basically. Okay, major use of statistics is to collect and use sample data to make conclusions about populations. We talked about that in the last section. All right. So I want to distinguish between two concepts. There is what's called a parameter. A parameter is a numerical measurement describing some characteristic of a population. So let's say, for instance, that I wanted to calculate the mean GPA of all students at Merced College. That would be a parameter because it's talking about the whole population. And there is a great trick that will help you remember this particular bit of vocabulary. I absolutely love that it works out this way. So parameters are about populations. Statistics are about samples. So if I wanted to calculate the mean GPA of students in this class is not a good representative sample of all of Merced College, but that's okay. That would be called a statistic because it's just measuring the mean for the sample, okay? So of course the trick is to help you remember that parameters are about populations, statistics are about samples. Two words that start with P, two words that start with S. I just love when that kind of thing works out, all right? Okay, talking about types of data, there is quantitative data. Quantitative basically means numbers. Okay. Also called numerical data. Consists of numbers measuring counts or measurements. Now you might think, well, what else would numbers stand for? Well, sometimes numbers might as well be letters, right? So they have one example in here that I like. The numbers on the back of sports jerseys, for example, do not represent counts or measurements. They're basically just labels, okay? So that would not be an example of quantitative data. That would be an example of, and here are a couple of examples of quantitative data, weights and ages. Okay, they represent measurements. Numbers on the back of sports jerseys are an example of categorical or qualitative data. So qualitative data are often words, just words, like male or female, but can be numbers as long as the numbers sort of don't really mean anything mathematically. If you would never think about doing any math with the numbers, like adding them, subtracting them, multiplying, dividing, or if you wouldn't, or if it wouldn't even make sense to put them in order. And jerseys are an example of that. The numbers on the back of sports jerseys, you know, there's no meaningful way to put those in order even. Okay, the best person on the team is not number 1. The worst person is not number 99, right? That's not the way it works. Couple of other good examples of qualitative data that are numbers would be like the channel numbers on the TV. Okay, they are not in any meaningful order. Okay, one other example maybe is phone numbers. Phone numbers are, you know, they don't mean anything as numbers. They're just labels, basically. And it doesn't even make sense to put them in order, okay? All right, working with quantitative data. Aha. So you have your categorical data, which is your names or your numbers that are just labels. And then you have your quantitative data, which is numbers that are actually meaningful as numbers. So those data can be broken down further into discrete and continuous data. So let me explain to you what the difference is. Discrete data, and I have my own way of saying this that I like. Discrete data result when the data values are quantitative and the number of values is either finite or countable. Now, countable might not mean what you would guess it means. And I actually reworded this a little bit from how it came from the publisher. The way that I like to explain discrete data is that it often answers the question, how many? How many? Okay. So here's, I think, just one example, the number of tosses of a coin before getting tails. That is definitely a how many question. 99.9% of the time, discrete data is just whole numbers. Okay, it doesn't necessarily have to be, but 99.9% of the time, it's just whole numbers. No fractions, no decimals, just whole numbers. Okay. Except notice that if you only have a finite number of possible values, that also makes it discrete. Okay. How many is discrete? Continuous answers the question, how much? How much? Hopefully you understand the difference. So continuous data result from infinitely many possible quantitative values where the collection of values is not countable. You would not be able to put them in a list. All right. And that usually happens with measurements. Measurements. The lengths of distances from 0 to 12 centimeters would be continuous because it can be absolutely anything along that spectrum. It could be 6, it could be 9, but it could also be 5.84, 7.21, 11 1/8. You understand the difference? Versus, you know, if it was discrete, we would probably just be talking about whole numbers from 0 to 12. All right, that brings us to levels of measurement. Another way of classifying data is to use 4 levels of measurement, and they come in this order from lowest to highest: nominal, ordinal, interval, and ratio. Okay. And these fit into the categorical versus quantitative thing also. Okay. Starting with nominal level, that is the lowest level of measurement. Nominal means your data is just labels. There is no meaningful way to even put them in order. So nominal level of measurement is characterized by data that consists of names, labels, or categories, and the data cannot be arranged in some meaningful order. And when I say meaningful order, I don't mean like alphabetical. All right. Alphabetical order is not meaningful in terms of what the things mean, right? It's just a convenient way to put them in order that everybody understands. Okay. Survey responses of yes, no, and undecided are a great example of nominal level of measurement. Another one, let's say that I'm collecting a bunch of data on Merced College students, and one of the questions I ask is, what is your major? Your major would be a nominal variable, okay? Biology, chemistry, psychology, education, okay? Those are all perfectly good majors, but there's no meaningful way to put them in order, okay? Except alphabetical, which is not meaningful, all right? Now, numbers can be nominal, okay? The sports jerseys, the phone numbers, the TV channel numbers, those things are all nominal, okay? All right, the next level up is ordinal. So you still can't really do any math with ordinal variables, but you can at least put them in order. So ordinal level involves data that can be arranged in some order, but differences obtained by subtraction between data values either cannot be determined or are meaningless. All right. My favorite example of ordinal variables, ordinal data, have to do with words and not so much with numbers. Freshman, sophomore, junior, senior would be an example of an ordinal variable. There is a meaningful way to put them in order, okay? Another example is course grades, A, B, C, D, F. Now, I'm not 100%, and let me just tell you up front that there is sometimes some gray area between these levels of measurement. You could make a decent argument that course grades are a little better than ordinal, you know, because people do talk about, oh, my friend got a grade that was 2 grades higher than mine. All right. Well, that person just subtracted. They found the difference between 2 grades. An A is 2 grades higher than a C. So that suggests that maybe it's 1 level up from ordinal. But, you know, I try to use, for example, on my exam, I try to use ones that are a lot more clear than that. Okay. All right. Then we get into the variables that are always numerical. All right. And the first one of those is called interval level. So we started at nominal, which is the lowest level. Then we went up to ordinal, and now we're going up to interval. So with interval level, it does make sense to subtract. Okay, the distance between things is meaningful. So that involves data that can be arranged in order, and the differences between data values can be found and are meaningful. However, what keeps this from being the highest level, which I'm going to tell you about in a minute, is that there is no natural 0 point, which also means that ratios are not meaningful with interval levels. So their example, and I have another good one, is the number of the year: 1000, 2000, 2020, 1776. This would be considered interval level because it makes perfect sense to say that the year 2000 is 224 years after 1776, right? That makes perfect sense. Everybody understands what that means. But it doesn't make any sense to say that the year 2000 is 2 times the year 1000. I mean, you can say that, but it doesn't really mean anything. Okay. There is a year 0. Actually, technically, there isn't. Did you know that? It goes from 1 BC and then to 1 AD. All right. No year 0. Okay. However, even if there is a 0 with an interval level, it's sort of a 0 that somebody made up and it doesn't mean anything. So actually, my favorite example of interval level is temperature, degrees Fahrenheit. Okay. There is such a thing as 0 degrees Fahrenheit, but it's just something that somebody made up, right? It doesn't really, especially with Fahrenheit, it doesn't really mean anything, right? 0 degrees Celsius, at least you could say, means something. It's the point at which stuff freezes. It's still, though, kind of made up, okay? You have negative values with interval level. That's something that you don't necessarily have with the next level up, okay? Does not make sense to divide. Think about temperature. An 80-degree day is not twice as warm as a 40-degree day, is it? That doesn't make any sense. Okay. All right, so that brings us to the highest level, which is called ratio level. In ratio level, there is a real meaningful 0, and you can do division. Data can be arranged in order. Differences can be found. So notice, each time you go 1 level up, you get to keep all the stuff that was good about the last level, all right? So we started with nominal, where you can't do anything. Then we go up to ordinal, where you can put stuff in order. Then you go to interval, where you can put stuff in order and you can subtract. And now we're at ratio, where you can put stuff in order, you can subtract, and now you can divide, all right? Differences and ratios are both meaningful, and there is an actual meaningful 0. Class times of 50 minutes and 100 minutes. It makes perfect sense to say that a 100-minute long class is twice as long as a 50-minute class. Makes perfect sense. Everybody understands what that means. 0 minutes is meaningful, all right? -2 minutes doesn't mean anything. I think that's something that I never really thought about before. You typically don't have negatives in ratio, but you do in interval often. You know, well, at least for temperatures and years, you know, there's negative numbers there. Okay. All right, so to summarize the levels of measurement, the lowest level is nominal. That's where you just have categories. There's not even any meaningful way to put them in order. Then you have ordinal, which is categories with some order. You just can't do any math like subtraction. Then you go to interval, which is where you have differences, but you don't have a natural 0 point, and it does not make sense to do division. And then finally, you have ratio. That's the highest level. You can put things in order, you can subtract, and you can divide. And division always comes with having a natural 0 point. And one thing that I will add to this, all right, forgive me because this is a little clunky. These two levels right here tend to be categorical. And I guess I could bring up a thing where I type that. I think that would work better. Actually, yeah, let's do that. These two are categorical. And the two on the bottom are quantitative. There we go. That wasn't too bad. Okay. Let's see. Okay, that brings us to so-called big data. Big data means, hold on a second, data sets so large and complex that their analysis is beyond the capabilities of traditional software tools even. Analysis of big data may require software simultaneously running in parallel on many different computers. So I can think of a pretty decent example of that. Picture a map of the United States and imagine that you are a traveling salesperson who has to visit 100 different cities, okay? There is a famous problem called the traveling salesperson problem that asks, in what order should the salesperson visit those cities so that their total distance, for example, is as small as it can possibly be? So obviously, like, they're not going to bounce back and forth between, you know, New York, Los Angeles, Miami, Seattle, Boston. They're not going to do that, right? They're going to probably hit the whole East Coast and then work their way in. It turns out that if you have a whole bunch of cities on the list, that is a really hard problem, even for a computer. Okay, so that's the kind of thing that we're talking about with big data. All right, it's in order to solve a problem like that, you have to have what's called a supercomputer that can run really, really fast, or you have to have a whole bunch of computers that are kind of dividing up the work. Okay. I have a feeling we're not going to be using that term very often because obviously we're not going to be solving problems with big data, not in this class. Data science involves applications of statistics, computer science, and software engineering, along with some other relevant fields such as sociology or finance. So data science is really, really related to statistics, okay? Missing data. What do you do about missing data? Well, number one, it depends on why is the data missing. A data value is missing completely at random if the likelihood of its being missed is independent of its value or any of the other values in the data set. So for example, let's say that your parents asked to see your grades and you have, you know, a bunch of good grades, let's say 80s and better, but there was one day you just, you know, weren't feeling it that day and you got a 30 on something. If you showed your parents all the grades that were 80s or better, but you left out the 30, I would suspect that maybe that data value is not missing at random. Well, maybe there's some other reason that one's missing. Okay. But you know, it also happens where things just get left out by accident. Okay. Maybe there's an 85 in there somewhere, and that paper fell out of your notebook for no particular reason. That one is missing completely at random. There's no special reason why it's that one and not some other one that went missing. Okay. All right, so how do you correct for missing data? One common method is to delete all subjects having any missing values. So let's say again that I'm collecting data on Merced College students, and I want to know, you know, what year are they in school, and what's their major, and what's their GPA, and how many units have they completed, and how many units are they taking this semester, a bunch of different things. And let's say for some reason I didn't have one of those things about one student. So one way I could fix that is to say, okay, well, I collected a sample of 100 students. 99 is almost as good. I'll just leave that one out completely rather than use some of their data, but not all of their data. Okay, so just leave that person out. Okay. Oh, I just thought of another example of where cases are deleted. So you know, in California, we love our ballot propositions. Okay, those of you who vote, every time we vote, it seems like there's this big long list of propositions that we have to vote on. The way that those propositions get on the ballot, citizens put them there. Did you know that? It's not the legislature, it's not the governor, it's citizens. And the way that you get a petition or a proposition on the ballot is with a petition. And these petitions, I've seen them, I've actually worked on getting people to sign them sometimes, have room for about 10 names, and they all have to be from the same county. Okay. And I learned something interesting recently, which is that if there's anything that's messed up with even one of those signatures, what they will sometimes do is just throw out that whole page. And then none of the signatures on that page count. Okay. Right, right. So you have to put your name, you have to put your physical address, which is not a PO box, and you have to use blue or black ink and this, that, and the other thing. And so the people who collect the signatures are trained to be very, very careful, you know, to give very clear instructions to the people who are signing, because if anything's messed up, the whole page might get thrown out. So that would be another example maybe of deleting cases. It's not that the data is missing, it's just that there's something wrong with it. Imputing missing values. So that means substituting values for them. And obviously you have to do that in a way that's, you know, honest. Right? So you try to find some other way to fill in that missing data point. Okay. One way to do that is if you know that there is a certain relationship between two sets of data, you know, think X is the number of hours you spend studying for the first statistics exam, that's X, and Y is your score on the exam, okay? So it tends to be true that the more hours you study for an exam, the better your score is. Okay, it's not perfect, but you know, it tends to go that way. So let's say that for some reason I knew that this person right here studied for 10 hours, but I don't have his score, okay? So what I could do, and we're actually going to talk about how to do this later in the semester, is you come up with a formula that if I put in the number of hours somebody spent studying, it will predict what their score is. And so if I could come up with a formula like that, I would just say, okay, well, the predicted value is 86, and so that's just what I'm going to go with. All right? That would be an example of imputing a missing value. And that takes care of section 1.2, 1-2.